Hello and welcome, everyone. My name is Nick Brimley, and I'm the Marketing Director for the Slag Cement Association. I will be moderating today's webinar, Insight into Chloride-Induced Corrosion in Cement Paste Containing Ground Granulated Blast Furnace Slag. Our speaker today is Mohammad Teymouri. Mohammad is currently a PhD candidate and graduate research assistant at Colorado State University, where he's involved in a joint program between the Civil Engineering and Construction Management departments. His research focuses on the study of chloride-induced corrosion of concrete structures. Mohammad was also a research winner of the 2022 Slag Cement and Sustainable Concrete Awards. If you have any questions during the webinar, we ask all attendees to please use the Q&A feature and we'll get to your questions at the end. And with that, I will hand it off to you, Mohammad.
All right, thank you, Nick, and hello, everyone. I'm Mohammad Teymouri. I'll try to go ahead and share my screen with you. Can you see my screen?
Yep, we can see it.
Okay, perfect. So first, I wanted to thank you all for taking the time and listening to this presentation. In this presentation, I will talk about the chloride-induced corrosion in general, and then I will narrow it down to my specific topic. So first, I want to thank you, my advisor, Dr. Mohammad Teymouri, for his support and giving me the opportunity to work on this project. This project is a funded project by American Concrete Institute Foundation, and we had a wonderful advisory team that helped us throughout this process. And I want to thank you, the Slag Cement Association, for the opportunity. So I will give a very general explanation about the chloride-induced corrosion, and then I will talk about the method that I use and the result. I will focus on how this result can be beneficial in the field. I don't go to the details or technical details about that because it would be boring for all of you. So let's start with the chloride attack. So the first question is that what is the chloride attack? Regardless of type of the chloride that we have, the chloride ions can penetrate to the concrete after a while because concrete is a porous material. And some of these chloride ions can reach to the surface of the rebar and initiate something called corrosion of the concrete. And why it's bad? Because first of all, we will lose the protective layer, the green layer around the rebars. It's pretty important for us because it can protect the rebars from corrosion. The next problem is that after the corrosion, we will lose some section or cross section of the rebars, meaning we will lose the capacity of our structure. And also the corrosion product that we have has 2 or 3 times greater volume compared to the original products. It means that we have cracking in the concrete. The protective layer that you can see here, it's called the passive layer. So we need to take in our mind that the pH of the concrete, the pore solution of the concrete and concrete in general is very high. It's around 13. And that's the main reason that these protective layer forms, and mainly it contains OH minus, and the main reason is the high pH. So remember that part. We have a high pH before having any deterioration. And this passive layer or protective layer remains intact as long as the pH is very high and we don't have any chloride in the environment. That's a really ideal situation. Almost in all of the structure in the field, we have some scenarios that can reduce the pH of the concrete. So the next question is that why this investigation is important? Because almost everywhere you can find the chloride. We have chloride ions in the ocean water. We are using de-icers, whether it's sodium chloride, magnesium chloride, or calcium chloride during the winter to minimize the risk of freezing, right? So let's see, this is a concrete bridge. So the columns are in contact with the ocean water that contains sodium chloride, and on the deck we apply de-icers. So we can see on bridges, marine structures, and roadways we are using de-icers and chloride ions. So we know that we will end up with the corrosion of the concrete structures. There is a report. So based on the Federal Highway Administration report, the cost of corrosion only for concrete bridges is insane. And based on the new report by Infrastructure Corp, we can see that almost 7% of the concrete bridges only in the US affected by the corrosion of the concrete. This is a global problem, but you can see even the reports in the US is crazy. So it's a big deal. And I took part in a presentation by Professor Angus. I stole two slides from him. You can see again, if you want to compare the corrosion of the highway bridges only in the US, is around 0.1% of GDP. It's insane. And this is the same for Swiss, in Swiss. Another thing is that with aging of infrastructure, probably in the foreseeable future, we have more problems, and we have a wave of need for replacement, rehabilitation, and repair. And we need to do a better job regarding that. If we don't want to spend the money of taxpayer for repair of corrosion. The next step is that what do we have right now? So in some of the standards like the ACI 318, which is a building code, if you check the table 19, we can see they provided some limit for the chloride content inside the concrete. So for example, for cast in place concrete, depends on the exposure condition, whether it's a dry condition, or in the worst case scenario, we are exposed the concrete structure in a moist. So we can see the range is something between 0.15% to 1% of the cementitious materials. And these are based on two tests that we have, water soluble test and acid soluble test. We don't have time to talk about them, but these are two most common practices in the field right now. If you want to assess the amount of chloride in the structure, you can have a core from the concrete structure, and in the lab you can do these water soluble tests and acid soluble tests to measure the amount of chloride inside your concrete structure. But these are not enough. As I said, we can find the chloride all over the place, in ocean water, in the soils, in the de-icing salt, and the admixtures. And actually, it shouldn't be happen actually in the admixtures, but sometimes we can see in some countries. And what are the most important measures to mitigate the chloride corrosion? There are lots of them. We can play with the permeability of the concrete, lower it down, play with that mixtures, increasing the cover. We can apply concrete coating. We have used concrete inhibitors. Those are good, but we need to keep in mind that those are cost limited. So if from the beginning we consider that we end up with the corrosion of concrete, we can do a better job. But let's go back to the mechanisms. My research focused on the chloride-induced corrosion initiated by the de-icers. When we send the trucks to the field and they applied de-icers on the concrete, we can see that some of these chloride ions will physically or chemically bound with the concrete mixtures, the cement hydration product, and some of them, which are the free chloride, will reach to the surface of the rebar and initiate the corrosion. So I need to talk about something called the chloride threshold. How much of this chloride will initiate the corrosion? It's a very hard question, because if you check the literature, which is a quite old investigation, but this is the same for the new ones, that you can see the amount of chloride that initiated the corrosion in the different concrete structures from different authors is vastly different. It's all over the place, from 0.5% to 3%. So right now, Colorado State University and my advisor is part of a round robin test for the ACI Committee 222 to standardize the test method for that. So if you want to know how does the chloride-induced corrosion look like, I want to show you a very recent project. I'm involved in a project of our Saunders construction in Colorado. I took this picture yesterday. You can see that there is a concrete stir in a civic center parking, and it's completely corroded, and the city shut it down for demolition and rebuild of this structure. And the main reason is the corrosion of the concrete because of the chloride. The budget for the demo and rebuild is $800,000. And it's interesting enough when you go to the city and ask for why did you select this de-icer? They said we don't have money to conduct research about different type of de-icers that they're using, but right now they have to rebuild because of the corrosion. And the main cause based on their investigations is the de-icer. So they apply too much de-icers and end up with chloride corrosion that you can see here. So it means that instead of spending money for repair and rehabilitation, it seems that there is a room to make wise decisions, specifically for the de-icers or the mixtures that we are using. So let me introduce you two different phenomena, which is very important for us. I don't want to talk about permeability or corrosion mechanisms. I want to talk about the things that happens inside the concrete mixtures and how the incorporation of the slag as one of the most common supplementary cementitious material can help the study. So we have something called chloride binding. I showed you that regardless of the type of the de-icers or chloride ions, the permeability of the concrete, the mixed proportion after a few years or months, let's say 10 years, the chloride ions can manage to enter to the concrete. And we have a combination of the free chloride, which is dangerous for us. Those can attack to the rebars and initiate the corrosion, and some bound chloride, some of them physically or chemically bound to the ions. So the bounding is a favorable phenomenon. Why? Because we have lower amount of these blue ones, the free chloride, that can initiate the corrosion. So how we can have the binding? So chloride ions can physically bound with the CSH, calcium silicate hydrate, one of the main composition of the concrete. And also some of them can physically bound with the AFMs or C3A, tricalcium aluminate, to form something called Friedel salt. This is pretty important because the more binding that we have, it means that we have lower free chloride in the pore solution that can initiate the corrosion, break down the passive or protective layer around the rebars, right? So it is favorable phenomenon for us. How we can improve that? If we have more CSH in the concrete, it means that we have possibly we have more binding, right? So incorporation of the slag help to consume the calcium hydroxide and form more calcium silicate hydrate. And also, if we use a slag that have high amount of aluminum oxide, it means that we have more C3A, so we can have more chemically bound chloride. But the problem is that we cannot take it for granted. The chloride binding is a reversible process. So if we have a drop in the pH, which is pretty common in a real case scenario, we can see that some of this bound chloride can return to the microstructure. The first question is that how we can see the drop of the pH. It's pretty common. We have carbonation almost everywhere. I will touch the carbonation, sulfate attack, and acid attack a little shortly. But if you want to know more about the sulfate attack, so I know that SCA has a webinar for the sulfate attack. I will encourage you to check it out. But at the end, because of the carbonation, sulfate attack, or acid attack, the pH of the concrete will drop to below zero, and that's the point that this reversible process starts. How does it look like? You can see that we had free chloride and bound chloride, and after the drop of the pH, the amount or concentration of the free chloride will increase. It means we have more chloride that can attack to the rebar or passive layer, initiate the corrosion. It means the higher risk of chloride-induced corrosion. We don't want it, right? We need to have more chloride binding in our structures. So let me show you what happened when we have, for example, carbonation. Carbonation is the penetration of the calcium or CO2 in the concrete, which is, you can find it almost everywhere. And then you can see some of this bound chloride and some of this free chloride here. When the pH drop, you can see the bound chloride due to the drop of the pH will release, and now we have more chloride to initiate the corrosion. This is the phenomenon that I'm working on. This is one of the most underrated phenomenon in the service life modeling, which from now on I will call it chloride desorption. Chloride desorption is a process that the chloride ions separate from the matrix right here, and we have more free chloride ions that can initiate the corrosion. So let's talk about the carbonation, sulfate attack, and acid attack in the field. These are the three most common phenomena. Almost all the infrastructures that we have, we will experience at least one of them, or sometimes a combination of these phenomena. So carbonation simply is a penetration of this carbon dioxide in the concrete and the reaction with the calcium hydroxide that we have in the concrete, and the formation of a very weak acid, which leading to the drop of the pH. For the sulfate attack, this is the same. We can find sulfate in the soil, in the seawater, in the groundwater. So it's pretty dominant. And probably the acid attack is the most famous one that can immediately and sharply reduce the pH. So when we have the reduced pH, it means we already lose some of the chloride binding, and it can accelerate the corrosion process. This phenomenon, which we call it the chloride desorption, it's not favorable, right? I explained that. The other problem is that we don't have enough investigation on that, and we are one of the first investigations or one of the first researchers that wanted to know the mechanisms. The main problem is that we have something called service life modeling for the structures. Right now, as far as we know, the chloride binding is considered for the service life modeling. It means that when you have chloride in the field or exposed to infrastructures, you think and you suppose that some of these will bound and will not participate in the corrosion. But the thing is that we have chloride desorption and this reversible process after a few years, which is neglected. It's pretty important, and we need to take it into consideration. Let me touch the lit review a little bit. I don't want to talk about the lit review because I don't have time for that, but I want to encourage all of you, if there is grad students watching this, please check VOS Viewer. It's a powerful tool for literature review. You can upload hundreds or thousands of the papers related to your research and see which topics have been investigated. So it will simply show you some clusters, the different topics, and the connection that they have. The bigger circles means that these topics have investigated a lot. So I just wanted to mention that if you are a grad student, take advantage of these tools. It's a very powerful thing. To be honest, it's not user-friendly. It takes time to work with that, but I think it's worth it because it gives you a clear idea about the knowledge gap, the topics that already investigated. We don't want to repeat another people's job or research, right? So it's a powerful thing. So based on the literature review that we had and checking the another standards, we found a couple of the knowledge gaps. I want to focus on the first one, that we don't know what is going on when the pH changes, and actually we have no idea about the chloride desorption mechanisms in Portland cement, and when we incorporated, for example, supplementary cementitious materials like slag. With that, we had some research question that, all right, let's say we have different type of brine solutions and different supplementary cementitious materials. What happened to the chloride binding first, and then what happened to the chloride desorption after that? So we define some objective for that. All right, first we will investigate the desorption for OPC and then supplementary cementitious materials, and then we play with the pH, a different range of the pH. It should be noted that in a field, we barely have a pH lower than 9. We don't have pH right 2 or 0, you know, because as long as that infrastructure that can work for us, the pH measurement, it matters. We cannot measure the pH for a structure that already deteriorated, right? So we need to take into consideration, for example, for a fully carbonated structure, the pH is around 9. So in this investigation, we played with different ranges, but at the end, I will present the only specific range that is practical in the field. So this is our methods. We selected our materials, and then we use 3 common brine solutions or deicers that recommended by the SNO practices in different states and different concentrations. Right now they send the truck, so it's hard for them to keep track of the concentration. So we wanted to have very low and very high concentrations. We queued sample for 56 days because we have SCMs. We wanted to make sure that all of them have developed their structures, and then we measured the chloride inside the sample and inside the solution, and then reduce the pH, and again measure the chloride ions. To back up our measurement by titration, we did a lot of analytical tests like XRD, TGA, and pH monitoring and visual observation. For each supplementary cementitious materials, we use 2 different replacement levels. And this is our setup. So actually we expose the paste sample to the brine solutions in a jar, in a glass jar. We cap them and make sure that the temperature is the same. And then frequently we measure the chloride ion inside the solution. I just want to mention 2 things. First of all, the slag that we use have a very high amount of aluminum oxide. If you are using different materials, take it into consideration. And one more thing that maybe somebody asked why we are using calcium chloride and magnesium chloride, because of the 2 reasons. First of all, both of them recommended by the Federal Highway Administration to be used as a deicer during the winter. And also it's pretty important for the state at the very low temperatures. The NaCl doesn't work alone. We have to use those. And these are the equipment that we use. We use the titration to measure the concentration of the solution. And also we use a couple of the analytical tests to make sure that we know the microstructure of the material. For the analytical test, I just want to emphasize on one thing. The parameters that you're using is pretty important. So if you are doing it yourself, take care about the parameters that you're using. And one more thing for the thermogrammetric analysis, the interpretation of the data is pretty important. I've seen a lot of papers that have the data but fail to correctly interpret their results. So make sure that you know the parameters and you know how to interpret that, and reach out if you have a question about those. I can help you because I learned from others, so I can pass it to you. So I want to touch the methods a little bit. I don't want to focus on that. I just want to make sure that you're on the same page. So we use different brine solutions with different concentration. We expose our samples or paste to these brine solutions. And after a couple of weeks, we measure the chloride ions inside that. This is for chloride binding, and this is one of the setup. For chloride desorption, we did the same thing for the first part, because if you want to know how much of these chloride disassociated from the matrix, first you need to know how much of that bound, and then you can measure the desorption. So we use a different range of the acid. Why different range of acid? Because we wanted to have different pH levels. And again, we measure the amount of the chloride in this step. The difference between this step and the last step give us how much of that chloride disassociated. Let's start with the binding. This is not the focus of the study, but we had to start with that. So when we compare the binding result for OPC and slag, we can see that when we, for example, let's start with the OPC. When we increase the chloride concentration, we can see regardless of the type of the brine solutions or deicers, the amount of bound chloride increase. And the most promising one is magnesium chloride. I will talk about that. But when we incorporated slag 25% and 50%, it is promising. We have more binding regardless of the type of the cation in NaCl, calcium chloride, and magnesium chloride compared to OPC. And even at 50% is higher than the 25%. So again, the binding is a favorable phenomenon because it can it can mitigate or hold some of the chloride ions to initiate the corrosion. So regarding the chloride binding, the slag is most favorable one compared to OPC, fly ash containing, and silica fume containing paste. So which one had the highest binding capacity for the solutions? I said magnesium chloride and calcium chloride and sodium chloride. And the main reason is because of the pH of the solution and the system for these two or these three solutions are different. We need to take it into account. And also they impact the structure of the CSH, the calcium to silica ratio. I don't want to go to the details because it would be very boring for you, but you need to have a clear understanding that we have different salt solutions. They can impact the pH level of the system, and also they can impact the microstructure of the concrete that we have. Specifically for the magnesium chloride, we can see formation of porosite or MSH, which is very porous material on the top. So when we have more porous material, it means we have more penetration and also more binding. So regarding the paste, I told you that the slag is the most favorable supplementary cementitious materials, even compared to the fly ash and slag. And the main reason is that the formation of the CSH, the more CSH that we have, the more physically bound chloride that we have. And also the slag that we used had higher aluminum oxide content. It means that we have a lot of AFNs that provide the opportunity for formation of the Friedel salt. If you remember, Friedel salt actually represent the chemically bound chloride formation, and all of them are favorable. So let's talk about, so we backed up our measurement by titration by different XRD and TJ. This is before exposure. There is no sign of the chloride inside the graphs. So what you can see is a Friedel salt formation, for example. We can see that. But after exposure to the brine solutions, let's start with the OPC. For example, you can see the formation of Friedel salt here, and this is for sodium chloride. And then we compare the peak for sodium chloride compared to the magnesium chloride. You can see the peak is different. It means the higher peak is the higher amount of Friedel salt. When we compare them, for example, for SG25, this is the Friedel salt peak, and you can see for magnesium chloride is a lot. So actually what we measured by titration is back up with the XRD. You can use only XRD or TGA or titration, but for the research, it's not recommended. You always need to back up your observation by different method to make sure that everything is correct. And here again, we saw that the formation of Friedel salt or the chemically bound chloride is way too higher for slag containing cement or paste compared to the OPC and also other supplementary cementitious materials. And the same thing for the TGA method. You can see the dips that we have for Friedel salt here for slag, 25% and 50% is way higher than the OPC. One thing that I wanted to mention is that the incorporation of slag helps the formation of the chemical bound chloride. The physically bound chloride is good, but they are more prone to disassociate from the matrix and return to the concrete and initiate the corrosion. And because of that, Friedel salt is pretty important because it's harder to break down the bond that the chloride ions have with the cement hydrix. And after the binding, we play with the pH. How? We add different volumes of the nitric acid, 5 milliliter, 10, 15, 20, and 25. And over time, we measure the pH. You can see at the first few hours or at the first few minutes, the pH drop sharply. But after a few days, we can see due to the buffering capacity of the space, mainly because of the calcium hydroxide that we have in the composition, we can see that the pH went up to around what it was. So this is the pH of the solution. NaCl started from 12. We added acid, a drop, and then because of the buffering capacity of the system, it returned to here. You can see the solid lines are for 5 milliliter. When we have the pH is dropped a little bit, for example, from 12 to 11 something. And this is for the same for calcium and magnesium chloride. The first thing that you can notice that the pH for these are different. This is the first thing that we need to consider. And the second observation is that when we add a lot of acid, for example, 25 milliliter, which is it's not the case in the real case scenarios, but we wanted to have it as a data. You can see that even for a very high volume of the acid, the pH went from around 0 to something called 4 or here for 6. This is not a real case because I told you that in the field, barely we have something lower than 9. So with that said, we wanted to know, all right, how much of these chloride that I showed you in the slide about the chloride binding is associated. So let's start with the sodium chloride because the amount of binding for these are different, right? We can see that for sodium chloride, for example, for the OPC case exposed to NaCl, almost 90% of the bound chloride dissociated. You know what it means? It means that what we consider in the service life modeling, that we neglected some part of the chloride from initiating the corrosion is completely wrong after a few years. So actually we are overestimated the service life modeling. And you can see when we incorporated slag 25% and 50%, this is almost the same. For the NaCl, we barely have a difference regarding the mixed proportion. But in almost all the states, as far as I know, we have a combination of NaCl and CaCl2 or magnesium chloride. For example, here at Colorado, we are using a combination of magnesium chloride and sodium chloride. Sodium chloride is the cheapest one, and that's why most people want to use that. When it comes to the calcium chloride, you can see in OPC, when we didn't have any supplementary cementitious materials, almost 92% of the bound chloride released. But when we incorporated slag, it's better, right? Because 72% release and almost 30% of the bound chloride remained in place. So those cannot participate in the corrosion. And for magnesium chloride, the performance of the slag is even better. So again, this is the result for pH of the 9. This is a real case scenario. For example, for the carbonation, the pH for the fully carbonated is around 9. So you can see that when we incorporated, for example, 50% of the slag, and then we have magnesium chloride as a brine solutions or deicers, almost 50% of the chloride ions after drop of the pH remain in place. This is pretty important. It means that the incorporation of the slag will help to mitigate the risk of the corrosion. And again, we can see that. So using the supplementary cementitious materials is a little bit risky because they consume CSH and the buffering capacity or the pH of the system drop a little bit. But when it comes to the chloride binding, which is a favorable phenomenon, we can see that the incorporation of the slag improved that. And also when it comes to the release of bound chloride, we have lower rates of bound chloride, which is favorable. And this is an observation that we had. So you can see for a very high volume of the acid or a very low pH, we can see the drop of the, we can see a very corroded layer on the top. This corroded layer is very porous. And then we can see another layer here that we guess this is the depth of the chloride penetration, and we have a neat paste. So even we have a very low pH in the system, it doesn't mean that all the paste or all the concrete cross section decomposited. It's not like that. Only a proportion of that will deteriorated, and the acid became weaker and weaker. So we have a neat paste always in the middle. And this is the mechanisms that we came up. This is one of my last slides. So I showed you that the real case scenario, we have concrete pavements. If we apply brine solutions like sodium chloride, everything is fine. The pH is high, but after a while, due to the carbonation, acid attack, or sulfate attack, the pH reduce, and that's the problem because we have a corroded paste here, and the bound chloride start to release from the matrix, and we have more chloride disassociation, but this is a reversible process. So we have chloride binding, chloride desorption. It depends on the pH because you cannot, for example, add acid forever to a structure, right? You can have carbonation forever, but it's a very slow process. And at the end, if I want to have some main conclusion, the first thing is that the chloride binding, the chloride desorption and neglected in the service life modeling. We need to consider that incorporation of the slag is good because of the two reasons. First of all, increase the binding and also inhibited the chloride desorption or disassociation of the chloride. And also, one more thing is that the incorporation of the slag reduce the release bound chloride in different deicers. So compared to the OPC and even compared to the fly ash containing materials. And the last thing we need to know is that the type of paste that we are using and the type of deicer can impact all of these processes. And magnesium chloride always show the higher binding and because of the formation of the MSH groove site and other impact that have on the structures. Like all the studies, we have limitations. We only use the pure salt solution for the first phase. Right now, I'm working on to using commercial deicers and inhibitors, and we use the dry paste. So it's not a real case scenario, right? We didn't have a freezing thaw process because it's a first step. First, we need to know the mechanisms, and then we can add other parameters to know it better. So we are working on the different projects to make sure that we can capture our real life scenarios. And then at the end, we can propose something that, all right, this is what we found. Please consider that. And these are the main references that I use for this presentation. Please feel free to reach out if you have any question for the test methods or process and everything. And these are the Q code for the two papers that we published related to chloride binding and desorption process. And again, thank you all. And I will take any question that you have.
Yeah, thank you, Mohammed. You did a great job. I've got one question here so far. The question is, how did you choose the sample size and shape?
That's a great question. So it depends on what are you looking for. So in our case, we wanted to focus on the paste. We didn't incorporate the aggregate because aggregate always have some noise and thing, right? So we focus on the first thing on the paste. And then regarding the size, you can cast the concrete beam. You can core from the real structures, like the staircase that I showed you. Next week or next month, I will go to take some core from that and do the chloride analysis for that. But with that said, it depends on your test setup, and some of the standard give you some shape and size for that. But regardless of that, the size of your sample or the shape of your sample, the condition is much more important. What did you use for mixed proportions? How did you cure that, and how did you expose them to the brine solutions or carbonation, everything that you have. But it depends on the test that you are looking for. But mainly I can say that the test will dictate maybe the size and the shape of that. But regardless of that, you need to know what are you looking for and focus on that. You can select different shape and size in the laboratory. One question that always people in the field, I had a presentation at Transportation Research Board, and all of them are from DOTs. And all of them said how you can validate your result with a real case scenario. And all of them suggested me to go there and take some course. So these are the valid observations. But if you want to do it in the field, you can validate your result with that. And I will go and do that shortly.
Perfect. We have another question here. Does the consolidation time or amount play any role in the binding and or the desorption rate or mechanisms of the samples?
And that's a good question as well. So consolidation, it means, let's look at it like that. We want to do tests on different samples, right? The main thing that we need to consider is that, are we doing the same thing for all of them? Because if we do consolidation differently for different samples, it's almost impossible to compare them, right? It means it's like that you use, for example, a slag in one of your sample, use fly ash in another, and want to compare them. That's valid. You can compare the impact of supplementary cementitious materials, but you need to make sure that your casting is the same, the consolidation is the same, the curing is the same. But yes, that's a good question, that we always need to have the same consolidation or same test procedure for all of them to make sure that we can compare them correctly or accurately.
Great. We got a couple more questions here. Any concern with the introduction of CO2 injection technology impacting the pH of the concrete related to this chloride dissociation phenomena?
That's a pretty good question. And as far as I know, my advisor is looking to that, and one of the grad students wanna see that. The main thing is that the phenomenon that I talked about, chloride binding and desorption, can be impacted by different factors. One of them is the pH. So the main point for my presentation or research, I don't care about what was the cause of the pH reduction. I want to see that the pH reduced, and then see and focus only on the chloride behavior or chloride content in the samples. But you are right that injection of the in the CO2 is a big deal. Maybe they have some advantages for that, but we need to take into consideration that when we have CO2 and also calcium hydroxide in the matrix, probably we have a very dilute acid that can impact the pH, and we need to take it into consideration that probably it prevent any chloride binding, which is not good regarding the chloride-induced corrosion. But that's a good question.
Great. I got one last question here. Are you aware of any study regarding the effect in low clinker mixes in which the pH is lower than the OPC?
So to the best of my knowledge, no. I need to check this and I can give it back to you. But as far as I know, I'm not aware that which one has the lower pH or the incorporation of that lead to the lower pH or not. But it's not hard to investigate. For example, I have a suggestion for you. If you have the samples with what you want to make, you can, for example, cast a concrete sample, put a hole with a drill on that, for example, 1 inch or 2 inch, and you need to put some water inside that for a couple of days. You make sure that you cap the hole and everything. And after, for example, 3 days, 4 days, if you have a pH meter or a pH strip, you can measure the pH inside that hole with the water. It can give you some idea about the pH of that and the low clinker mixes compared to the OPC. And it will give you an idea. But no, I've never worked with that. But I have a suggestion for you that it's a piece of cake. You can do it very quickly, and you can compare your result with the OPC. You can cast one OPC and cast one of your sample. Do this simple experiment. I can send you the article that give you more details about the pH measurement process for different sample sizes or sample modes, if that helps.
Awesome. Well, I want to once again thank Mohammad for speaking today, and I also want to thank all of you for attending. You have Mohammed's email address up here. If you have any lingering questions, also You can reach out to me directly at info@slagcement.org. Thank you, and that concludes today's webinar.
Great. Thank you all. Thank you, Nick.